Welcome. In this video I will be talking about how to determine the activation energy for pyrolysis reactions from thermogravimetric analysis experiments. The video builds on the previous one and I suggest to watch it first. For the computations, the Python package FireSciPy is used. It can simply be installed via pip. The code is available on GitHub. In the Git repository you can also find this notebook that I am demonstrating here. For details have a look in the previous videos and also in the video description. Let's start with a little bit of theoretical background. The Kissinger-Akahira Sunose method is used here to determine the activation energy over the course of the reaction. It is a well-established isothermal method and should be preferred over Coates-Redfern or Ozawa-Flynn-Wall. And this important distinction is made here that the activation energy is called apparent and is denoted by an uppercase E and a lowercase a in the subscript. From experiments like TGA alone, it is in general not possible to determine the fundamental reaction mechanisms. They are basically only truly known for models, where the user already knows the input. I would like to mention some considerations on the data collection. This should help you then to get the most out of your assessment. To employ the isoconversional methods to the best of their abilities, data should be recorded from multiple temperature programs. There can be isothermal or linear heating rates. Linear heating rates are commonly used to deduce the apparent activation energy, and isothermal experiments to get an indication of which class of reaction models to use. At the very least 3, better are 5 or more temperature programs should be used. For linear heating rates, the lowest and the highest heating rate should be about a factor of 10 apart. For example, 5 Kelvin per minute for the lowest and 50 Kelvin per minute for the highest heating rate. Remember that we want to use the TGA to determine the decomposition behavior or specifically the pyrolysis reaction. This requires that the impact of energy and mass transfer processes is as low as possible. The energy transfer can be influenced, for example, by the amount of sample material used. Larger amounts of sample mass can lead to a delay in heat up of the sample and therefore lead to a temperature shift in the conversion plot. To ensure a low impact of the heat and mass transfer processes, mass downscaling runs can be conducted. They start with the highest heating rate that is intended to be used during the experiments. For this example, I am using data from experiments with polymethyl methacrylate or PMMA. Initial experiments were conducted at 60 Kelvin per minute and a sample mass of 12 milligrams. The normalized mass loss rate is determined and plotted against the sample temperature as shown here on the left hand side. The mass is reduced and new runs conducted. We can see that the reaction shifts to lower temperatures with reduced sample mass. The optimal mass is found when the peaks are in superposition. Here we stopped at 1 milligram without reaching convergence. Thus, the next step is to either reduce the sample mass further or reduce the heating rate. In this example, a new mass downscaling is conducted for a lower heating rate of 30 Kelvin per minute. You do not necessarily need to go to such low temperatures. You could also try to go for 50 Kelvin per minute or 45 or 40. This is a thing that you have to try out with your device and also the sample material that you are investigating. Again, for reduced sample masses, the reaction shifts to lower temperatures. However, now the 1 milligram and 2 milligram samples are in superposition. Based on this assessment, we can now choose the 1 or 2 milligrams. They can then be used for the experiments also at lower heating rates. This procedure is based on the ICTAC recommendations. When you write an article or your thesis, you should provide a plot like the one on the right hand side in support of your choice of the sample mass. Further information is also provided in the ICTAC recommendations linked below. Now on to determining the activation energies. As first step for processing the experimental data, the path to the files is defined and the investigation data structure is set up. The loop in line number 17 reads the files containing the experimental data. During the experiments, the data has been recorded in degrees Celsius. They are transformed here into Kelvin as is required by FireSciPy. Each file is stored inside the data structure. The data is sorted by the condition, which is the heating rate. There is a further distinction by the repetition. Then the pandas data frame with the raw data is added. A data type needs to be selected between integral or differential. This is necessary because different processing methods have been designed for each. Typically, TGA provides integral data, where you have the initial sample mass at 100% and then there is the S-shaped decay when the reaction is happening. Devices like DSC or MCC record differential data. The KAS method that is used here to determine the activation energy is designed for integral data. Methods for the differential data will be added later. Lastly, the unit of the heating rate is provided so that FireSciPy can convert it to Kelvin per second if it is necessary. Then the column headers of the raw files are mapped to known headers for the following processing steps. The reason is that the manufacturers of these devices use different column labels. So that means we do not know beforehand what type of device you have and also what the column labels look like. And with this step here, the data can be unified. Finally, the repetitions are combined. This computes the averages and standard deviations of the temperatures and the sample masses for any given heating rate. These averages are then later used for the kinetics computations. Now the conversion levels are computed for the averages of the heating rates. With this, we are at the same state that I manually created in the previous video with the data from the models. The now following steps are the same. Define and compute the conversion levels and compute the activation energy with the KAS method. Here the development of the apparent activation energy over the conversion is plotted as the result. For a single step reaction, the data points should form a nearly horizontal line. The average over these points is the apparent activation energy of the corresponding reaction step. Here we can make out at least two reactions, one in the beginning around 200 kJ per mole, and the main reaction with about 220 kJ per mole. It can also nicely be observed why often the leading and trailing 5% are cut off. In the initial 5%, some erratic behavior is visible. This is the result of noisy data from the experiments. The statistics are now also more interesting, especially at the beginning and the end. We also see that the root mean square error is not zero anymore. The combined data can nicely be accessed, for example, to create the commonly used mass loss rate plots. Again, also the standard deviation is available so that you can integrate it into your plot. As already alluded to earlier, the number and values of the temperature programs are an important factor of this assessment. I would like to demonstrate this here. Please also refer to the previous video. For the isoconversional methods, the activation energy is estimated from a linear fit. A large difference between the lowest and the highest heating rate pushes the data series further apart. See for example the purple data points at the top and the blue ones at the bottom. More temperature programs provide more data points for each fit. These fits are indicated here by the black dotted lines. This allows to better capture the underlying trend, which is important because the slope of each fit is used to determine the apparent activation energy for a conversion level. I've illustrated this here by fitting the data points of only the two lowest heating rates. A notable difference is visible in the slopes between the black and red dotted lines, which leads to differences in the apparent activation energy. With that, thank you very much for your time and have a nice day.